Welcome back to the class on HVDC transmission system. In this lecture, we are going to discuss about the reactive power requirement in a HVDC system. Why the reactive power is required in a HVDC system, that we are going to see in this lecture. Conventional control strategy. In HVDC system, there are two converters are there. One is rectifier converter, another one is the inverter converter. This is rectifier station, this is the inverter station. This is the transmission line. Between the supply and the rectifier station, transformer is there. In the same manner here also the transformer is there. In normal operating mode of a HVDC system, this rectifier converter will be operating at a constant current, whereas a inverter converter will be operating at a constant excitation angle control. But when you are operating these two converters with this control system, it will require a less amount of reactive power. If you find the equation for the reactive power, that is also depending upon the real power. Now we are going to see how do you calculate the expression for the real power and reactive power in per unit only. So first we are going to define the sum of the base values for the power as well as a voltage. The base converter voltage is nothing but a how much maximum voltage given by this converter is nothing but a base converter voltage, that is VDB equal to 3 root 2 by pi Vn, where Vn is nothing but a line voltage here. We can get this voltage by this converter when the alpha equal to the 0. Base DC current IDB equal to rated DC current. So the base DC power equal to P suffix dB equal to NB into VDB into IDB, where NB is nothing but a number of converters we are connected in a series in a one station. Generally at the rectifier station, how many converters were connected in a series? The same number of converters were connected in a series at a inverter station also. Said the base AC power equal to VB equal to Vn. The base AC power equal to base DC power, that is equal to root 18 by pi NB VB IDB. All these values we have defined previously. The average DC voltage given by this converter in per unit, that is equal to VD bar equal to V bar cos alpha minus RC into ID. This is nothing but a voltage drop across a leakage reactance of a transformer. VD bar equal to VD by VDB, ID bar equal to ID by IDB, RC bar equal to XC by 2, where XC is nothing but a the per unit reactance of a transformer on its own base. Power factor is given by the, from this also we can calculate the power factor. Divide the throughout equation by V bar, we are getting the power factor, that is equal to cos alpha minus RC bar into ID bar by V bar. This is the power factor of a converter. Now the real power PD bar equal to V bar into ID bar into cos pi, QD bar equal to V bar into ID bar sin pi. The same equation also we can use for the inverter station also. In place of alpha, you have to replace the gamma. Now we are going to draw the how the reactive power in a converter will be changing as the real power is changes. That we are going to see here. Now to draw that waveform, we have taken the alpha equal to 15 degrees, XC bar equal to 0.2 per unit, V bar equal to 1. Now on the x-axis we have taken the real power, on the y-axis we have taken the reactive power. At alpha equal to 15 degrees, if you draw a graph means this is graph. If the firing angle of the converter we have increased to 30 degrees, we are this is another graph. Nothing but as the firing angle is increases, the reactive power demand at a converter also will be increases very sharply if you observe these two waveforms. So it is better to maintain the firing angle is lesser at a rectifier station as well as a inverter station. But if you maintain the firing angle very less value for the rectifier as well as inverter means, at a rectifier the mode of operation will be frequently changing. Suppose if we maintain the low extension angle for the inverter means there is a computation problem will be occurs in a inverter. Now come to this point. Now the rated power factor is 0.866. This rated power factor is reduced to 0.851 if the firing angle is 18 degrees. At 18 degrees, the reactive power is 0.6 times the real power. So the power factor of the converter is highly depending upon the firing angle, whereas the firing angle increasing means the reactive power demand at a converter also should be increased. It is going to control the real power. The reactive power demand at a rectifier station or the inverter station, it is also depending upon the voltage. Suppose due to the some fault or something, if the voltage decreases, the reactive power demand at a converter will be increased. But practically, we have a tap changing transformers keeping between the supply and a converter. By changing the tap changing, we are maintaining the constant voltage. So you can assume in HVDC system, the constant voltage applied to the rectifier as well as a inverter. In case of alternate control strategy, the reactive power demand at a converter we can decrease it. How we are going to decrease it means we are limiting the control region of a rectifier as well as inverter at a constant voltage. The constant voltage means for a rectifier the alpha is minimum, for inverter gamma is minimum. So by means of control system we have to maintain the alpha is minimum for the rectifier and gamma is minimum for the rectifier. We have to maintain the DC link current also constant at a maximum value. Then we are getting this type of characteristics for the HVDC station. This region of characteristics is bounded by the minimum gamma for the inverter, minimum alpha for the rectifier, and a constant DC link current. The constant DC link current, DC current is nothing but this characteristic, which is represented in semicircle. The constant voltage at a buses if you are maintaining means the characteristic will be passing through the origin. So this characteristics we are getting by maintaining the constant voltage. So with respect to this characteristic, we can say very easily that the rectifier we can see as a load with a lagging power factor. The inverter we are seeing as a generator with a leading power factor. If there is no voltage suppose provided at a buses, our stability region will be decreases. In HVDC system, we are seeing the rectifier as a load with a lagging power factor. See, this is the reactance of a transformer. This is the rectifier place. From the rectifier, we are taking the PD and QD. This is real power. This is the reactive power. Now the voltage we have taken as a reference. Current lags this voltage because it is a lagging power factor. This is the E phasor. The same manner, if we draw the equivalent circuit for the inverter means, so this is nothing but inverter where we are giving a real power as well as reactive power. That's why we are seeing the inverter as a generator with a leading power factor. This is the transmission line. This is the line where we are tapping the power. Now if we draw the phasor diagram for this one, again you have to take the voltage and the reference. But in this case the current leads the voltage. This is the E. Delta is nothing but the angle between the V and A. Pi is nothing but the angle between the voltage and current. Nothing but power factor angle. Now we are going to find out the expression for the real power. From this phasor diagram, if we find the projection of E vector and V vector on a current vector, both are equal, and find the value of V, we are getting the E cos of delta plus pi by cos pi, where pi is nothing but a power factor angle. The power given by the rectifier, that is equal to V into E into B sin delta. Now substitute this value in the above equation, simplify this one. Here B cos delta plus pi into sin delta divided by cos pi. E square into B divided by cos pi constant take outside. This we have to reduce cos C cos D formula. So we are getting this expression that is equal to cos square B by 2 cos pi sin 2 delta plus pi minus sin pi. The maximum power we can transfer on a link only when delta equal to delta maximum, that is equal to 45 degrees minus pi by 2. Now in place of delta you substitute the delta m. In this expression simplify we are getting E square B by 2 into tan delta m. Suppose if we take the power factor angle equal 30 degrees, the maximum power given by the rectifier are passing through the DC link, that is equal to Pm equal 0.2887 E square B. So in this expression you take the pi equal to 30 degrees, that value of substitute here and simplify you are getting. This is the maximum amount of power that can be transmitted through the DC link. Suppose if the converter station, if we are supporting with a capacitor, then this power will be increased. Expression for the power in which we are supporting the buses with a capacitor, that is given here 0.2887 E square B divided by 1 minus BC by D, where BC is nothing but a susceptance of a capacitor which is connected at a bus. So from the above analysis we can say very easily that the reactive power if you are supplying at a converter, there is a large increase in a real power transmission. Now how we are going to achieve that means by selecting a reactive power source which is connected at a bus. That is one method. The second method is that we have to design a control system such a way that it can able to supply the reactive power within the converter. Now these are those characteristics will be modified in this manner if we are supporting with a reactive power. A dash is nothing but A B and A dash B, which is representing the constant lagging reactive power characteristics. A C and A dash C is representing the constant leading reactive power characteristics. Suppose if the converter is operating at this point, if you supply with a QN reactive power, then the converter will be operating at unity power factor. Suppose if the converter is operating at this region, then if we provide a reactive power of 2 QN, then the power factor angle of the converter will be changing from pi to minus pi. So in this manner, we can increase the power transmitted through the DC link. If we find the expression for the DC current as well as the DC voltage, ID equal to P suffix B N by V into square root of tan pi square plus PD by PDN whole square. The first area ID equal to P QDN by V into square root of 1 minus PD by PDN plus PD by 2 PDN sin pi whole square. Expression for the DC current in both areas of characteristics. Now the DC link voltage VD equal to PD by ID. Lowercase letter we are using for the per unit value. For V equal to 1 per unit and pi equal to 30 degree. Now we are going to draw a graph as the real power is changing. How the DC link voltage and DC link current and firing angle changes. These are the characteristics of a rectifier station. The same equations we can use for the inverter also if you replace the alpha with a gamma. How the DC link voltage and DC link current and extension angle will be changes as the real power is changes, that we can see here. This is for the rectifier station, this is for the inverter station. So thank you very much for watching this video.